Welcome to aminacademy.com. In physics, let us discuss about mechanical properties of solid fluids, some solving problem. We'll do some theoretical questions here. Explain why the blood pressure in human is greater at the feet than at the brain. We know that pressure is due to height, it increases. That means P is equal to rho H rho G. Here H is the height column. Now the height of the blood column is more for the feet as compared at that for the brain, because from that body itself some height is there. For example, 6 feet man is height 6 feet. That blood pressure is more in feet because it is more distance from the blood column. So the height of the blood column is more for the feet as compared to the for the brain. Consequently, the blood pressure in human is greater at the feet than at the brain if he is standing upright. Second question, atmospheric pressure at a height of 6 kilometer decreases to nearly half of its value at the sea level, though the height of the atmosphere is more than 100 kilometer. Here, that actually atmospheric pressure is reducing if you go up and up in the sea level. But here the question says atmospheric pressure at a height of about 6 kilometer decreases to nearly half of its value at the sea level, though the height of the atmosphere is more than 100 kilometer. Here, the variation of air density with height is not linear. Actually, the pressure variation is air density is not a linear one, so pressure does not reduce linearly with height. That means if you go double, it reduces half, like it won't be a linear. The air pressure at a height h is the formula P equal to P0 minus, that is actually you can write in power form here, equal to P equal, the pressure function is P0 and e power minus AH. Here is a pressure function in terms of height is it's not a linear function, so it is this function is it's not a linear function, so it is P0 represent the pressure of air at the sea level and alpha is the constant. Next question. This exponential function, due to exponential function is it's not a linear, so this variation is not like given there above. Next, hydrostatic pressure is a scalar quantity even though pressure is force divided by area. Here pressure formula is force divided by area, but it is a scalar function because pressure is in everywhere is directions changing, because you are standing on a floor, your pressure distribution is in every directions in the floor. So due to applied force on a liquid, the pressure is transmitted equally in all direction inside the liquid. That is why there is no fixed direction for the pressure due to liquid. Hence, hydrostatic pressure is a scalar quantity. Suppose you are having on ball, it's a floating. You are pressing down the ball inside the liquid, or sometimes you are inside the swimming pool. Your hydrostatic pressure is for your every direction. So we cannot say it is in a constant direction. So it is not a vector quantity, it's a scalar quantity. Next question. Explain why the angle of contact of mercury with glass is obtuse while that of water with glass is acute. Here, let the drop of liquid L be poured on a solid surface S placed in air A. Therefore, here if TSL and TSA be the surface tension corresponding to the solid liquid layer, and solid air layer. Here TSL and TSA is given, and theta is the angle of contact between the liquid and solid. We know that formula TLA, liquid air space, tension in liquid air space into cos theta plus TSL equal TSA. This is the formula. From that we can get it cos theta equal TSA minus TSL by TLA. For the mercury glass interface, TSA is greater. That is solid to air is lesser than tension in solid to liquid. Therefore, cos theta is negative. Cos theta is negative. Thus, theta is an obtuse angle, that is more than 90 degrees. For the water glass interface, TSC is greater than TSL. Therefore, cos theta is positive. Therefore, here theta is acute angle. That means the reason the angle of contact of mercury with the glass is obtuse while that of water with glass is acute because of these conditions. Next question. Water on a clean glass surface tends to spread out while mercury on the same surface tends to form drops. Put differently, water wets glass while mercury does not. Here, water easily wets the glass surface, but mercury is not. Water on a glass surface tends to spread out, that is, water wets the glass because force of cohesion of water is much less than the force of adhesion due to the glass. In case of mercury, force of cohesion due to mercury molecule is quite strong as compared to the adhesion. That means the contact of glass and mercury coefficient of adhesion is less than the coefficient of cohesion. That means what? Molecule itself, mercury molecule itself more strongly attract force due to the glass. Consequently, mercury does not wet glass and tends to form drops. Here, the surface tension because of cohesion force between the molecules of mercury is very high than the water itself. So water easily spread and mercury is not. Surface tension of a liquid is independent of the area of the surface. Here, surface tension of a liquid is the force acting per unit length on a line drawn tangentially to the liquid surface at rest. Such H as force is independent of the area of the liquid surface there. Therefore, because this is a length function, this is force acting per unit length is a surface tension. So it is the surface tension is not bothered about the surface area. Since H as a force independent of the area of the liquid surface, therefore surface tension is also independent of the area of the liquid surface. The same liquid having different area have the same surface tension, not with area changing. Water with detergent dissolves in it should have small angles of contact. Why? We know that the clothes have narrow pores or spaces with which act as a capillaries. capillary, small capillary tubes it acts, that is holes, narrow pores act as a capillary tube. Also, we know that the rise of liquid in a capillary tube is directly proportional to the cos theta, means angle of contact. That theta is the angle of the contact. Theta is small for detergent. Therefore, cos theta will be large because theta here, cos theta is reducing, that cos theta is reducing, cos theta will be increasing. Due to this, the detergent will penetrate more in the narrow pores of the clothes. That is why for washing the clothes, we are using detergent to, because to penetrate, that means the water should penetrate more inside the pores of the clothes. A drop of liquid under no external force is always spherical in shape. You know that the drain drop and you are dropping your water very slowly, it acts as a drops of water, spherical shape. We know that any system tends to remain in a state of minimum energy. Is the absence of any external force, that means there is no air flowing more. Suppose the external force is very less, then it is, suppose if external force is not acting on the water drops, the given volume of liquid, its surface area of, and consequently surface energy is least for a spherical shape. It is due to this reason the liquid drop in the absence of an external force is spherical shape. That is why raindrops are mostly spherical shape. Now let us fill the blanks here using the words from the list appeared in the each statement. Surface tension of a liquid is generally decreased with temperature. Surface tension is decreasing with temperature. Decrease. Next, viscosity of gases with temperature. Viscosity is increasing. Viscosity of gases is increasing. Increased temperature, whereas viscosity of liquid is decrease. Next, for solid, for solids, the elastic models of rigidity, the shearing force is proportional to shear strain. Shear strain, while the fluid it is proportional to rate of shear strain. Next question. For a fluid is in steady flow, the increase in flow speed at a constriction follows from conservation of mass. Conservation of mass, while the decrease of pressure there follows from Bernoulli's principle. Next question. For the model of a plane in a wind tunnel, turbulence occurs at a greater speed. Greater speed. than the critical speed of the turbulence of an actual plant. We have done. Please subscribe our YouTube channel.